And welcome to this session of ClimaCon. I'm Dr. Marshall Shepard, and today I want to talk about why we're using the vantage point of space to measure things like precipitation and other aspects of the climate. And I have two experts from Tomorrow I.O. that certainly can help us with that question. Joe Munchak, who is a senior atmospheric data scientist at Tomorrow I.O., and Ricky Roy, a senior scientist in the space and sensors division of the company. Guys, thank you for joining us on this session. Joe, I want to come to you. Tell us a little bit in a 101 layman's term, what Tomorrow I.O. is up to from the vantage point of space as it relates to precipitation and perhaps other things.
Yeah, well, thanks, Marshall. It's great to be here with you. So, right, Tomorrow I.O. is getting prepared to launch a constellation of satellites that will measure precipitation globally at a refresh rate that we really haven't been able to observe before. And there's many reasons to do this. The main reason to go to space for this is because that enables us to observe really the entire globe from the standpoint of precipitation. So, of course, depending on where you are in the world, you may or may not have access to high quality weather radar data, which is what most people use to tell whether it's raining or not right now, or used for short-term forecasts. So some areas have good radar coverage, but most areas don't. In fact, the vast majority of the world doesn't. And so we could go through the process of installing ground radars everywhere. We needed them everywhere that there's people, but that's getting into some pretty remote environments where there may not be reliable electricity or other necessary infrastructure to maintain the radars. And the cost is really quite high to build them and for the number that we would need. And so the reason you go to space is that you can now fly a bunch of satellites, and these satellites will be equipped with the same radar, and that can cover the area much more quickly because the satellites go circle the globe every 90 minutes. And we'll be able to see a wide enough swath that we probably, with only a handful, dozen or so of these satellites, see the globe close to every hour, depending on the exact instruments that we do, which is what we're working on. We really want to be able to give that coverage, as high quality and as frequently refreshed as possible.
Yeah, Joe's with the weather science team at Tomorrow I.O., and he's preparing to make use of data from the world's first commercial multi-sensor satellite constellation for precipitation. But he's not new at this. Joe, prior to joining Tomorrow I.O., was at NASA's Goddard Space Flight Center, where he was a research meteorologist, and he served in several roles, including deputy project scientist for ground validation on a mission called the Global Precipitation Measurement Mission, or GPM, which I know a little bit about as well. In fact, I was deputy project scientist for that mission while at NASA. Joe earned his bachelor and master's degree in meteorology from Penn State and a PhD from Colorado State. So clearly the company has pulled together a team that knows what they're doing. And someone else on that team is Ricky Roy. Ricky has spent a good deal of his career prior to Tomorrow I.O. at NASA's Jet Propulsion Lab, or JPL, which is at Caltech. He was part of the NASA postdoctoral program fellow. He really sort of understands the sensors side of things. He has a bachelor's degree in math and physics from University of Puget Sound and a PhD from the University of Washington. So, Ricky, I really want to come at you. So Joe's kind of set the stage here for what's going on and why we're doing it. And we're going to get more into the so what factor throughout this session. But how do we do that? I mean, how do we measure precipitation, winds, and precipitable water vapor from the vantage point of space? I know most people may be familiar with things like rain gauges, which we just heard about, but most of the planet is not land. In fact, it's mostly ocean or inaccessible lands like mountains and deserts. So how do we take these instruments on spaceborne platforms and make these geophysical measurements?
Yeah, that's a really great question. I think it really boils down to the fundamental techniques that make up the field of remote sensing. It's basically asking the question, from a remote platform, how can I measure a quantity that's very far away from me by measuring something really far away from it? And the typical approach is to send out a signal, an electromagnetic wave at some frequency or some wavelength, that will interact with the region that you're interested in measuring. And then that signal, when it comes back to you, there's information about that region of space sort of encoded, you could say, in that signal. And so what our job is from the sensor point of view is to, first of all, derive those signals appropriately, which for a radar means sending out a very specifically designed electromagnetic pulse that propagates through space. It kind of bounces around, for instance, in the clouds and precipitation, maybe off the surface, and it reflects back to our sensor. And we actually catch that reflected signal back at the sensor. And we very precisely register that signal that comes back. And then we go through some estimation algorithms to derive, for instance, how much precipitation did that signal interact with. And so it's an indirect way of trying to measure something very granular. For instance, how much liquid water is within this precipitation cell, which will really tell you about things like the rainfall rate, the propensity to flooding, things like this.
Yeah, I have taught classes on satellite remote sensing and radar meteorology. We aren't directly measuring rainfall in the same way that rain is falling into a rain gauge when we're using these satellite-based sensors. But as Joe well knows, being a deputy project scientist for ground validation, we get pretty close on certain scales in terms of understanding what's falling from the ground based on these more indirect measures. Now, one of the things that we should sort of elucidate here, and I'm Dr. Marshall Shepard moderating today, is we have active sensors and passive sensors. Active sensors send microwave energy out. So if you've gotten a speeding ticket from a police officer, perhaps that was using a radar, they were firing a signal. It was bouncing off of your car, and some of that energy is backscattered to their radar or their LiDAR. And in that case, it probably was a Doppler system, and so there were changes in frequency. But that's an active sensor because you were sending out a signal. We also use passive techniques where we sort of quote unquote listen for radiation or emissions coming at various frequencies, whether they be infrared or microwave. Joe, what is the so what? Who are the users of these sort of indirect measures of rainfall, which we can then in turn use to paint a global picture at fairly high time resolution? Why do we want that? I mean, why do we need that?
Yeah, so first of all, just to explain a little bit more about passive sensor, your eyes are passive sensors. They're just looking at what the visible wavelengths of light are. And obviously we have some intuition there. We can see different colors, and we can, kind of see what, by the shape of things, what's there in front of us. And so it's the same principle with microwave remote sensors, except that those are using much longer wavelengths that the human eye can't see. But nevertheless, still interact with things and tell us something about what the sensor is looking at. And so when I talk about microwaves, I'm talking about the same wavelengths that your microwave oven uses to cook food. And the reason that they do that is because they interact really well with water molecules and heat that water up. And so all the water that's in the Earth's atmosphere in the form of raindrops and water vapor emits these same microwaves naturally. And the sensor is just detecting where those are. And they can also detect ice particles, depending on the exact frequency we measure at. There's other gases like oxygen. And so you can really configure these sensors to observe a really wide variety of properties in the atmosphere. And it's really all about picking the right frequencies and designing and building a sensor that can go up there. The advantage of passive sensors is that they, because we're not sending out our own energy, they require a lot less power to run. And so they're inherently going to be cheaper, and we can build more of them. And when you have more sensors up there, you can get a much better revisit rate. And because precipitation in particular changes on such rapid timescales, from 5 minutes to the next, it can be raining really hard and suddenly dry up, or vice versa. And so we really want to hit that refresh rate from the satellites as kind of the key objective of this sensor constellation that we're designing in order to get at the precipitation problem.
Yeah, I mean, ideally, and as someone that has sort of been in this sort of scientific realm myself, in a perfect world, we'd put an active radar on a geosynchronous satellite that's staring at the same place on the planet all of the time. That's typically what you see when you're looking at a weather satellite and you're watching a hurricane, perhaps approaching the coast in the summertime. It's a geosynchronous satellite, some 35,000 kilometers up. It's basically orbiting at the same rate the Earth is rotating, so it looks fixed compared to the Earth. Unfortunately, because of those power and mass requirements that Joe just talked about, we just can't do that right now. And so the approach is to take this sort of large constellation effort. Again, the NASA GPM mission is a large, fairly expensive, long developing mission that's in orbit. But Tomorrow IO is approaching this and moving the bench forward, if you will. Ricky, tell us why and how this constellation approach of small sensors really moves the needle beyond sort of where NASA started this party, if you will.
Yeah, a lot of it kind of boils down to, we'll say, differing priorities. So at NASA, the main priority is to develop what we would call kind of science quality instruments that are going to perform very, very accurate and very detailed measurements of a specific type. And often it's really not geared towards operational use cases. It's a lot more about studying fundamental properties of the atmosphere. And for instance, improving our parameterization of these cloud and precipitation processes and weather and climate models. And that's not exactly what our main goal here is at Tomorrow IO. We're kind of coming at it more from the perspective of the gap that ground-based radar fills, which is an operational use case that gives us real-time actionable information about precipitation. And so that levies different requirements really on the two different satellites, one being something like a GPM, a very expensive, large mission, and then the other being our constellation of small satellites, which will have capabilities that are comparable with GPM, but our main goal is not to perform these sort of high science quality observations. We want to be able to provide people with actionable information. And so that might.
Who are some of those people, though? And this is a question for either. I know the national weather, the stakeholders like National Weather Service, but I imagine there are others out there that want this sort of high resolution, detailed precipitation information. Who are some of these people?
Yeah, so outside of the sort of obvious use case of individuals would like to know if a storm is coming their way so they can prepare. Some of the more industry related applications could be like in aviation. And that's a particular case where radar is very well suited to provide very valuable information for decision making, because airplanes fly through three-dimensional space. And it matters not just where in latitude and longitude the precipitation is, but also how high in the atmosphere. And so it's very useful for them to have really a three-dimensional picture of the precipitation field that they could, for instance, navigate around or navigate through. And that's also true of clouds in some situations as well. And those are really unique measurements that only a precipitation radar can provide. There are many other ways to sense precipitation, like for instance, at the surface, or getting sort of an integrated measure of how much liquid there is in the whole atmosphere. But radar gives you this very unique three-dimensional structure that you can kind of play around with and look at in a visualization sense. So airlines is another very apt application of this data. I'm sure Joe might be able to think of.
Yeah, I know Joe from the application standpoint, water resource managers, emergency managers, those thinking about flash flooding, I could imagine would be of value. And you might say, well, we have radar. We do, but we don't have radar on the ground everywhere. And so you need these sort of complementary observations from space, because again, I think we all get biased by pulling out our apps because we live in places where there are radar, but keep in mind that most of the world is not radar accessible. And so this is really providing not only capacity for the US, but literally around the globe. Joe, do you want to add to that discussion of who some of these users are?
Yeah, absolutely. So you're right. Like we had this perspective that, we can just look at the radar. But there's plenty of places, even in the United States, where that's not the case. Anywhere, a lot of times there's mountains that block the radar beam. And so if you're separated, from the nearest National Weather Service radar by a mountain range, you're not really getting high quality radar data. If you're getting any at all, there's still some well-known gaps, even in major metro areas like Charlotte, North Carolina. that aren't really well served by weather radar. So this is really valuable even in the United States. And right, we mentioned obviously the use cases of warnings, flood warnings, severe storm warnings, monitoring hurricanes as they develop over the ocean where there is no ground radar. One of the things that I've learned about from working at Tomorrow.io is just how diverse our customer base really is and how many use cases I wouldn't have thought of. So another example is there's a lot of industrial processes that depend on really exact temperature controls. And if there's an outside processing plant, they need to anticipate changes in temperature. And one of the things that we've heard from customers is, hey, when we have a forecast of a storm rolling through, usually the temperature drops, during a summertime thunderstorm. I think we've all experienced this. And if we can give them that information by knowing exactly when the storm's going to roll through, which is something the radar can warn us about, they can adjust their control processes and potentially save a lot of energy and a lot of money by being able to anticipate that change in environmental temperature.
Yeah, that's, it really, I'm Dr. Marshall Shepard, and we're talking with Joe Munchak and Ricky Roy about the wonders of using emerging technology Tomorrow.io is investing in and developing to measure precipitation. And this is where I want to go with this next. And some of the technology that you're talking about, I understand, is not just anchored in precipitation observations. I believe that there are other climate related or atmospheric or oceanic related measurement capabilities as well. Ricky or Joe, can you talk about, maybe we'll start with Ricky. Can you talk about what are some of the other capacities that your space program at Tomorrow.io is addressing beyond precipitation?
Yeah, sure. There are a few key areas that we're looking at. So one has to do with the active sensor that we're utilizing, which is this Ka-band precipitation mapping radar. And as we've been talking about, really the main application area here is quantifying precipitation on a global scale with very high temporal resolution, that rapid refresh that Joe was talking about. But in addition to sensing precipitation, these radar pulses also actually reflect off of the Earth's surface, and they scatter in a very specific way that can be very much indicative of different conditions of the relevant surface. So this depends whether you're looking at ocean or looking at land. But if you're looking at ocean, in a crude sense, you can kind of think that the roughness of the ocean surface is going to affect the way that this radar beam scatters off of it. In one extreme, you might have a very, very calm ocean surface that will act like a mirror, and your beam will just reflect off of it and go out into free space and you'll never see it again. But when the ocean surface is very coarse, you'll actually get a lot of diffuse scattering, and you'll get more of that beam energy reflected back to your sensor. And so you can actually deduce things about the ocean state, which is very indicative of the near surface atmospheric state, how windy it is right above the ocean surface. You can deduce that actually just from looking at the strength of that radar signal coming off of the ocean. And you can see similar effects on land when certain land surfaces are covered, for instance, by snow or not. That'll have a very clear signature in the radar scattering that we can use to actually estimate some of these surface properties like snow cover, potentially soil moisture, vegetation cover. These are very much signals that are kind of embedded in our radar measurements that we want to utilize.
Joe, do you want to add anything to that?
Yeah. So first of all, on the radar measurements, one of the things that really enables this is having that frequent revisit, so we can compare how this surface scattering has changed on a time scale of a few hours. When you have to wait a few days, like we do with the GPM, it's sometimes tough to tell, well, was that a change because it snowed or it rained, or maybe the snow already melted, and it's tough to really understand things when you don't have the frequent revisit from the constellation. But even aside from this, on the passive side, I mentioned earlier, those microwave sounders, they do a whole lot more than measure precipitation. In fact, the main reason they were designed was to measure profiles of atmospheric temperature and water vapor. And NOAA has gone back, used these for 20 or 25 years or longer.
And let me interject before you keep going. And that's because we've typically relied on weather balloons soundings to get that information. And those are only launched every 12 hours or so and at specific places around the planet. So they really don't give us the space-time coverage that we need.
That's right. Yeah. So it's for weather forecasts, especially we kind of take for granted these days how accurate weather forecasts are out to 5 or even days or even longer. And the reason that's possible is because we have really nice numerical models of the atmosphere, so we can simulate on a computer all of the physical processes that are happening, and much faster than it takes them to occur in nature. But we also have really good observations to initialize them. And for a long time, right, the weather balloons were the only source of observations, or ground stations. But to get the winds and the temperature and humidity all the way through the atmosphere, which you need to make a weather forecast because the different levels interact with each other, we needed these weather balloons. And so that was a limited system, because the same problem with radar, we were limited to a certain number of ground stations. They cost money. Right now, there's actually a helium shortage, so we're having fewer weather balloon launches than we otherwise would have. And so, again, remote sensing kind of took over to fill in the gaps, and we started launching microwave sounders to measure these temperature profiles, again, by picking these frequencies right where the oxygen emits radiation naturally, or water vapor molecules. And through some remote sensing techniques, we can devise profiles of temperature and water vapor. Now, they're not as accurate as the weather balloons, but we get the global coverage. So they're all pieces of the puzzle, and there is all extra information that goes into the same forecast models. And so right now, you get coverage from these sensors about every 4 to 6 hours, depending on how close you are to the poles. And so we're trying to improve that to every hour. So that's, basically increasing the number of observations going into our computer models by close to a factor of 10. And so we're expecting not only improved real-time precipitation estimates, but also improved weather forecasts out to 5 days or longer from our constellation.
And I want to just sort of tag on to something Joe just said. Our weather forecasts are really good, by the way. You always hear the joke, oh, it must be nice to be a meteorologist and get paid to be wrong half the time. Come on, go look at the numbers; they're pretty good. I'm at a university, and we have a pretty good football team. But imagine if a football player, a kicker, made every field goal and perhaps missed one in the bowl game. It's a really good kicker, but probably people remember the one miss in the bowl game. And I think that's how weather forecasting is. Now, having said that, we know that there are places where we can improve our modeling capacity out to a point. I mean, there's some theoretical limits based on some physics and nonlinear theory and some things that we can get into some real technical details about. But we know, that you hear the European model versus the American model debate and all those types of things. It really gets at what Joe was just talking about, data assimilation. There's quite a bit of satellite information being assimilated into these models, no matter whether it's the European model or the American model. And so it's quite critical that we fill those gaps, space and time-wise. And I think that's what much of what Tomorrow IO is trying to get at with their new space program and their capabilities. Now, I'm talking to two colleagues that, like me, were at NASA, and that's a federal agency. I think that's who many people assume do these types of things, but we're in a new era in which private companies have entered the game. So I'm curious, from both of your perspectives, what is it that attracted you to Tomorrow IO, a private company getting into the space-based Earth observation business? I'll start with you, Ricky.
Yeah, so first you touched on something pretty important there. That is, I think that there are two independent problems that have to be solved to improve forecasts with these observations. So there's the first one, which is develop a sensor that makes very well calibrated and very reliable measurements. So you have those measurements, but it's not clear, or it's not obvious that you can use those measurements yet to improve the forecast. And so there's a whole side of it, which is, how do I squeeze as much juice as possible out of this lemon, which is the observations, to improve the forecast, right? And that's the job of the data assimilation folks. And one thing that's very unique about Tomorrow IO is, as this kind of new space weather technology company, we're very much vertically integrated across these sectors. And so, yes, we're developing the whole space program and the satellites to make those observations as reliably and accurately as possible. But we also have an entire in-house data assimilation team developing very novel mathematical methods to leverage those observations to the maximum extent possible. And that doesn't even exist, I would say, in a lot of the federal agencies like like NASA, you'll have the instrument teams very much siloed away from a lot of the applications oriented teams. So that was certainly one thing that attracted me to this very ambitious program, in that we can we're actually informing our spacecraft development and our payload designs based off of how we are analyzing that those observations will improve precipitation nowcasts and forecasts, which is very exciting to be at the point.
How about you, Joe?
Yeah, so I think first of all, there's really three, I think, concurrent revolutions going on maybe for the past 10 years that have made this possible. First, we've got certainly the explosion of cloud computing, which is what lets a private company run forecast models in the first place, because these are really power hungry endeavors. And I think like a lot of the original purpose of developing computers back in the 1950s was to make weather forecasts. So it's really resource hungry, but cloud computing lets us do that on demand and not have to invest in hardware and maintenance and all of that. The other revolution is really, I think, the really big drops in the cost of access to space that have happened, thanks to companies like SpaceX and other new space companies that are really lowering launch costs. Miniaturization of technology with CubeSats is another big part of it. And then I think the third part's the machine learning revolution, which is happening. And that's really letting us kind of get to that problem that Ricky was mentioning, which was just squeezing as much info out of the measurements as we can without having to build these really expensive theoretical models for every single type of measurement. So really three revolutions that kind of are converging right now. And just seemed like something really exciting to be a part of. And also, being a scientist with a global precipitation measurement mission, it was always my dream to develop an even more robust real-time constellation. And when I saw that Tomorrow I/O was planning to do that, I thought, why not join them and contribute as much knowledge as I can.
I'm Dr. Marshall Shepard. I'm talking with Dr. Ricky Roy and Dr. Joe Munchak, both of Tomorrow I/O, a new company. They're newish. They've been around for a while now, rebranded recently, but doing some really interesting things in the space-based observation for the planet standpoint. I mean, we use the vantage point of space to understand Earth, to improve life on Earth. And I think that's something that we want to understand. As we start to sort of wrap up this session, Ricky, I want to come to you first, and then I'll let Joe have the last word. What are you most excited about in this sort of next 0 to 2 year time frame? What are the big opportunities and challenges that you see? What keeps you waking up in the morning to tackle this problem?
Yeah, that's a great question. So on the largest challenges, we have a very ambitious mission in our space program to build an incredibly capable sensor, relatively in a quite small size, weight, and power and cost form factor. So we're pushing really the frontier of what you can achieve, I think, in a small sat. And so there are a lot of technical challenges that come with that. But that's kind of why personally I got into this business in the first place, is solving really hard or seemingly impossible problems. But I only do.
We didn't start out doing Rubik's Cubes because they were easy, right? They were a challenge.
Oh, exactly. Yeah. But I will say I only like to do that if it's towards a mission that I really believe in and something that I'm passionate about. And the access to precipitation and really just severe weather information that we're going to be able to provide, I think, to the whole world is a very encouraging goal to be working towards. And so it's a rewarding program to be working on in that regard. I think there are a lot of benefits across a lot of sectors of society that will be had when we're successful with this mission.
How about you, Joe? I'm going to lob the same exact question to you.
Yeah, so that's a great question. So yeah, I mean, I'm really looking forward to when we get those first satellites launched and being able to use that data right away. So obviously the big challenge for me on the weather science side is preparing our models to be able to ingest that data right away. And so we're doing a lot of experiments with simulated data, with the GPM data that comes from NASA. We're learning a whole lot. A lot of what we're doing really couldn't be possible without that NASA GPM mission. So we really definitely owe them a lot in terms of just the foundational knowledge. that we've built. And yeah, I think that's just like Ricky. I look forward to this and every day. And I took this job in the first place because I think it's an opportunity to make a real impact and provide some real benefit to societies where the access to weather information and precipitation information in particular is kind of lacking right now.
Yes. One last question before we go, though, because we may have some young listeners of this session. Yeah, I think this is a non-traditional realm for someone that's thinking about being a research meteorologist or a research engineer going into sort of the private sector. What kind of skill sets do you sort of recommend? I mean, you're working. This is a new company, new approaches, very well integrated across many different disciplines. From two people that now are working in a private, essentially weather-related company, what would you tell sort of your young selves to prepare you for this kind of a job? What would you do differently to prepare for it? I'll start with Joe on this one.
Yeah, so I'm definitely playing catch up on a lot of machine learning. I think that's something that people going to school now probably have a lot more courses to pick from. It was kind of off in the realm of statistics and computer science, and I was more of a hardcore meteorology and atmospheric science major when I was
taking Fortran and C back in the day when I'm older than you all, but maybe it's a Python world now. But now you're saying AI and machine learning is where it's really at.
Yeah, so I mean, the language you use is maybe not as important as what you use it for. Mm-hmm. Although most of the machine learning world is built around Python these days, which makes it easier. It's just for purposes of trying to debug code, I think it's a lot easier to do that in Python than Fortran. But I think that everyone, that's our generation or older probably had to suffer through that. So hopefully,
exactly. And even some of those same weather models that we were just talking about earlier are still written in legacy Fortran code, believe it or not, although many students these days use Python.
That's right. And there's performance reasons for that. And a lot of times, it's if it's not broke, don't fix it attitude. But yeah, I think that, being strong in statistics and methods, obviously, like the languages may change from time to time. So that's something that I need to keep up on. But really, I think the number one advice I have is just, having an attitude that learning doesn't stop when you finish college, because the requirements are going to change, and the skill sets that are needed to solve these problems are going to change over time. And you have to be flexible and just have that attitude that if there's a better way that's come about, or something that's interesting, go ahead and learn it, and and try to apply new methods to old problems. And sometimes you can get a lot farther than you could have with the previous way of thinking.
Yeah. What about you, Ricky? What would you tell young Ricky is like, okay, I'm going to work for Tomorrow IO one day. Here's what I better do differently.
So I personally took a very indirect route to where I am now, which I maybe wouldn't or maybe would recommend to young folks. But I'm essentially a physicist pretending to be an engineer that also sometimes pretends to be an atmospheric scientist. And if you had asked me maybe 6 years ago what I would be doing, I thought I would probably be a professor at a liberal arts school teaching physics. So I've taken a few right turns there. But the consistent thing is always trying to tackle hard problems that will be meaningfully impactful. And along the way I kind of pursued that was to always study the fundamentals and learn just the most basic aspects of the field that you're trying to tackle. So it started with physics, started doing a bit more of that in engineering and atmospheric science at JPL, and I'm still continuing to be able to do it at Tomorrow IO, which I love. It has a bit more, I think, of an academia feel than it might appear from the outside. We have very technical and academic oriented discussions every day, like Joe and I. And that part is incredibly enjoyable. So it's probably cliche, but following what interests you most, I think, will always pay off in the end. It might be hard, to find the opportunities, but as long as you're persistent, it can definitely happen. And it's exciting to see the commercial sector stepping up in that regard. It's sort of like a new age of companies that are filling the old Bell Labs or HP roles, where R&D happens in the commercial sector and not necessarily just in academia and government.
Yeah, and that's a great point to end on, because again, you may be watching this on a smartphone, or you may be going somewhere today using GPS. You may take a heart medicine for an ailment that you have. Those things didn't poof come out of existence. They came from R&D. And so we're seeing the evolution of R&D and Earth observations from space as it relates to weather and climate and so forth. And so I think you're now seeing sort of the next phase with efforts like Tomorrow I.O., which both Ricky and Joe are engaged in. So I want to thank both of you for participating in this session of ClimaCon. And I want to thank Tomorrow I.O. for organizing ClimaCon 2022. And hopefully you've learned a little something today. And thank you. And we'll end the session here. Take care.